Okay, so last time we saw, so let me just recap the first two lectures. So in lecture 1, we just discussed black hole thermodynamics. We saw that black holes have entropy. And in lecture 2, by the way, there was some problem with the recording, and I did a new recording at home, and it should be up whenever Dimitri puts it up. So last time we first discussed this correspondence principle of Horowitz and Polchinski, like how strings become black holes. Okay, they both have exponential growth of states as a function of the energy, but the actual function in the exponent is different, and there's a certain point where the functions agree, and that's called the correspondence point. Okay, so roughly speaking, the string states go as e to the m, and the black hole states go as e to the m square, and it's in some units. Once you put those units, you equate the two. That's when the string becomes the black hole. And then we saw that if you want to have examples where you want to study the growth of states precisely, including the agreement of these functions, it's a good idea to focus on supersymmetric states because there's some function which is roughly like the number of states, which doesn't change as a function of the moduli. Okay, so that's what we studied last time, and this function I'm talking about, this counting function, is not just a number, but in the simplest example for the Witten index, it's the number of bosons minus the number of fermions. That only counts the number of zero energy states of a certain quantum system, of a given quantum system. And if we want massive states like we want for applications to black holes, then we should consider more sophisticated indices, and that's what we discussed in detail last time. So here's a recap of that part of the lecture. So we're considering supersymmetric theories in asymptotic flat space, four-dimensional flat space, and in order to get massive states whose number, whose index is protected by supersymmetry, we need to go to extended supersymmetry. That means that n counts the number of supercharges in units of the basic multiplet of supercharges, which is 4. Okay, so n equal to 2 means there are 8 supercharges in the theory. Okay, and in such, so n equal to 1 is minimal. In such theories of extended supersymmetry, the states, which are the representations of the algebra, are labeled by the mass as well as another charge called the central charge. Okay, so that's the new thing about extended supersymmetry, and there's a relation that mass is greater than or equal to the absolute value of the central charge. Okay, that is for generic representations. So all states obey that. And then there are special BPS states. There's a special class of states called BPS states, or supersymmetric states, which preserve a fraction of the supersymmetry. So in n equal to 2 theories, there'll be half BPS states. I'll fill up the table soon. And those have the property that the mass is equal to this. They saturate this inequality. The mass is equal to the central charge. Okay, maybe absolute value. Okay, so that's what I want to remind you of. And in particular, we'll take four-dimensional theories and we focus on states that preserve 4 supercharges. Okay, so in different theories, they'll preserve different fractions of supercharges. That's sort of the minimum thing we want to do. Okay, so let's fill up this table. So n equal to, so last time I worked out n equal to 2 theories which have 8 supercharges, n equal to 4 have 16, and n equal to 8 theory has 32, and these two, so this had worked out, this had written the table, and this was an exercise. So I'll just fill up the answers. I'm assuming all of you have done the exercise. So here there's a central charge. So in this case, for n equal to 2 theories, there was one complex number z. For n equal to 4 theories, there was 2 complex numbers, and n equal to 4, it was something like that. And we can even order, I mean, just to avoid confusion, we can order them like this. You can always order them like this. Okay. Now, if you look at these states which preserve 4 supercharges, then you ask what fraction of supersymmetry is preserved in these various theories. And here it's 4 out of 8, so it's 1/2. Here's 1/4. Here's 1/8. Okay, so these oftentimes these black holes and these states are referred to as 1/4 BPS black holes or 1/8 BPS black holes. But I'm saying this to avoid confusion that they're actually part of different theories. Okay.
But can I just check, preserved means it's annihilated?
Preserved means it's annihilated. As a state, it means that Q and Q dagger, okay, alpha and alpha dot equal to 0. Okay. That's what we mean by, so for bosonic symmetries, if you have a quantum state, preserve would mean that under small variations, and the generator of the symmetry would keep the state invariant. Right? Just think of a sphere. The sphere preserves a rotation. That means that under the rotation, the sphere doesn't change. In the quantum theory, that's the analog, and for supercharges, it's the same thing. All right, good. So that means that the rest of the supercharges are broken. So 4 are preserved, so 4 are broken here, 12 are broken here, and 28 are broken here. Those broken supersymmetries give rise to massless Goldsteiny. So those are fermion 0 modes. And if you just do trace of -1 to the f, because of those fermion 0 modes, you get 0. And last time we saw how to engineer indices, special BPS states. One more thing I want to say is that there's a certain index you can write. I want to write that in a bit, which gets contributions from these states. Okay, so before that I want to write this. Here it was m equal to z, and here it was m equals z1, and then, okay, so if you really want that, it's, okay, I'll put this here. So the next thing we saw last time was that that there's a way to absorb these fermion 0 modes by calculating not trace -1 to the f, but something slightly more subtle. So there was supersymmetric index. It was called the helicity supertrace. Which was B2n, was defined. So if you have a state which preserves, so let me write it first. So if I have a state which break 4n supercharges, then they receive contributions from this B2n, which was traced over the full Hilbert space, -1 to the 2j3 times 2j3 to the 2n. And sorry, I shouldn't have. So this is a repeat, but I'll say it again because it's important. So this B2n receives contributions from states that break 4n supercharges, and no contribution from states that break more than 4n supercharges. Okay? Less than, you have to sort of do it experimentally. Sometimes they might, sometimes they won't. But usually when you break more supersymmetry, the number of states is more. So you don't care about the things. So let's say here you have 1/4 BPS states. The index, the correct index will be B6 like we saw last time. It will get contributions from 1/4 and maybe from 1/2. You don't care because there's not a lot. And for the leading entropy, it doesn't matter. But the main point is it does not get contributions from generic states. Okay? So now let's do this. So here, remember, so this preserves 4, breaks 4, so n is 1. So the relevant index was B2. Here it preserves for breaks 12. So N, so the relevant index is B6. Okay, there's 6 pairs of 0 modes. And here it was B14. Okay. And this, okay, so that was sort of a recap of last time. Okay, this the first two rows part of this was an exercise, which I hope you've done. Otherwise, for the moment, you can take it. If you, by the way, if you don't manage to solve the exercise, they're not supposed to be research problems. So please come and ask me. They're supposed to be like 10-minute problems. All right. So this whole discussion was, so it used only the asymptotic notion of conserved charges. So you had some picture like this. So remember, we had two pictures of black holes in string theory. Okay. Here you had some microscopic picture. Okay. And what these are some strings or brains, excitations, okay, whatever you have of string theory. These are the microscopic. Remember, this was G string very small, and this was G string very large. Okay, so here there's no gravity. You've switched off gravity, and you can't read this. These are the microscopic strings, brains, or other microscopic excitations of string theory. Okay. And now we should start to be more precise. On this side, you want a black hole in 4 dimensions. Okay. If you want a 4-dimensional black hole, if you have, let's say, type 2 string theory, which lives in 10 dimensions, then you should think of this in some compactification of type 2 theory on a 6 manifold. Okay. And depending on this manifold, you'll get theories with different number of supersymmetries, which are preserved. Okay. This I don't know how many of you know. Can I have a show of hands again? MSc students probably will not know this, so just take this as a fact. But I want to check how much string theory you've learned. In the first lecture, I checked a few things. Do you know, for instance, that if I compactify type 2 theory on a certain manifold, I'll get n equal to 2 or n equal to 4 theories? Or not really? Can I just, okay. Okay, then just take this for a statement. So let me just give you an idea. So type 2 string theory, all of you have seen. This is some 10-dimensional string theory with 32 supercharges. Sorry, I'm moving a lot. Maybe it's not useful. With 32 supercharges. Then you want, so what do? You compactify it on some 6 manifold. And depending on the properties of that manifold, you preserve some you preserve some amount of supersymmetry. So what that means is, what does supersymmetry mean? Supersymmetry means you need some killing spinner. Right? The killing spinner means that the geometry that you compactify on must be such that it allows for a killing spinner. Not all manifolds allow for killing spinners. Okay? And depending on what the manifold is, there will be some or the other number of killing spinners. Okay? So the simplest compactification manifold M6 is just a 6 torus, just completely flat. There's no curvature. And there you preserve all the supersymmetries of the n equal to 8 theory. It's as if you take 10 dimensions and 6 of them, you just make them compact. Here there is a certain class of manifolds called K3 manifolds, which are 4-dimensional, 2 complex dimensional. So this is T2 times K3, and here this is some generic Calabi-Yau. Okay. We won't be really using any of this, but if you go into sort of exploring this subject, you'll see this soon enough, and I wanted to put it up there. Okay. So this M6 is one of those, and these strings or brains must be, if you want to think of, if they have to become a black hole, a strong coupling, then in 4 dimensions they must be point-like. Okay. These are extended objects in string theory, so they must wrap the internal in that wrapping cycles of M6. Okay. So you can have a string, for instance. If I have a T6, you can have a string wrapping one of the cycles. So if I have K3, it has 2 cycles. You can have some D2 brain wrapping the 2 cycles. Okay, so these are extended objects, but in 4-dimensional space-time, you want to think of them as some points. Okay. Now those objects, those extended objects in string theory carry their own charges. Okay. That also assume, at least in 10 dimensions, you might have seen in some beginning course, that a string, for instance, when it winds around a circle, there's a winding number. That's a charge. If I have a brain, it can wrap a certain 2 cycle, but the number of times it wraps, that's a charge. Okay? So those extended charges, so the charges of these objects, which are intrinsic to string theory, those become the central charges. Okay, in the algebra. When you translate, when you do the compactification, and you just work out what are the various charges, and then ask how does it play with the superalgebra, you'll find that those central charges are really charges. That's why they're called central charges. Okay, so that's the microscopic description, and we'll pick this up in a bit. But on this side, you have something else. Here you have a low energy description like we started with in lecture 1. So you have a metric, you have some number of gauge fields, you have some number of scalars, you have lots of fermions, and so on. Okay. That I believe most of you have seen. That there's some low energy description, there's an effective action of all these fields in 10 dimensions. When you compactify it, you get a 4-dimensional effective action. And now what does supersymmetry mean? Supersymmetry in this sense means that low energy effective action has a supercharge which is some killing spinner which is generated by a killing spinner. Okay. So those are the supersymmetries of the theory. And then you write black hole solutions in the black hole. Right, black hole solutions, that means that the metric is not flat anymore. There's some curved metric, and you have to ask how many of these killing spinners are preserved by the black hole metric. Preserved means exactly that. You have a metric, this killing spinner generates a certain transformation of the metric and of the fermions, and you have to demand that you'll have an equation of this side, that delta epsilon of all the psi's will be some function of the, meaning it will be some action on the fermions which depends on the bosonic coordinates, and you have to demand that this is equal to 0. Okay, that's what supersymmetry would mean. And in that sense, so here there's a d slash which, so this roughly, let me write it out, will be something like gamma mu d mu plus dot dot dot, maybe there's some r mu nu times something like that. Okay. All kinds of things, F mu nu, R mu nu. That's what the killing spinner equation looks like. The only point I want to make here is that this right hand side depends on the background metric and bosonic fields. So putting that to 0 will give you an equation for the bosonic fields. Okay? So that's the sense in which you say whether a certain solution preserves some number of supersymmetries or not, okay, depending on what epsilon is. So it turns out that there is a class of black hole solutions which preserve 4 supercharges of the 8 or 16 or 32, and those are called BPS black holes. Okay. And here you should ask, what is Z? So here the whole description should be in terms of this effective field theory. There's a metric, gauge fields, scalars, and fermions. And the charges are all, it's 4 dimensions point-like, so the only charges possible are electric and magnetic charges of the gauge fields. Okay. So all the central charges, Zi, is either Q or P of the gauge fields. Okay, there's a bunch of gauge fields, and some of them are special, they will feed in, some linear combination are special. They will be identified with the central charges. Okay. Any questions about this? Because here I'm trying to sort of say a lot of things without showing you how it works, because it's yet another whole discussion. Both of these are separate discussions. For instance, this, this you can, this will take another couple of lectures, but maybe I'll give you a reference. A good reference is a book, should I write it? maybe I write it here. So a good reference is a book called Supergravity by Friedman and Van Prooyen. Sorry. Okay. Okay. Now, yeah, of course. Please ask.
Could you repeat the last?
Yeah, this thing about Z and Q. Yeah. So I'm saying that in general, like even with this much information, you should try to process and ask the following questions. That I'm saying that the whole description is in terms of the low energy effective action. So anything I say about the system must be in terms of these fields. Okay. So now we're making all these statements about algebras, supersymmetry algebras and central charges. You say, what is Z? You haven't shown me what Z is. I'm saying Z will be identified with the charges carried by these gauge fields. That's the only statement. So there'll be lots of gauge fields. Okay, that depends on the compactification, and a certain combination, if it's an n equal to 2 compactification, then there's one special combination of the gauge fields, that's called the graviphoton, and the charge of that will be Z. If it's n equal to 4, there'll be two special combinations, which will be Z1, Z2, and so on. Okay. Please ask more questions. Let me just pause.
And after the equal, what are the letters there?
Q / P, this is like not really an equation. This is like more like I'm saying Z will be some either electric or magnetic charges. Because those are the only charges in the system. Here, you have lots of charges. In string theory, you have these extended objects. Okay. Not just gauge fields, but you have 2 forms, 3 forms, whatever, depending on your theory. Okay. And you have these extended objects which carry those charges. Okay. Those will be identified with Z. And when you compactify it, those should be point-like. So they should wrap something in the internal direction. Okay. All right. Now the main point here is that, so let's say Z is equal to Q as is to be concrete. Let's say there's one Z and one Q. This theory, yeah.
This Q is not the supercharger.
Sorry, thank you. So I should call it small q maybe. Thank you very much. Yeah, I also probably called it big Q there, but it's no. So far I haven't. That's good. So let's try to call it small q for electric charge. If you study this theory of supergravity and write down a black hole metric and demand that it preserves, let's say, 4 of the 8 supersymmetries of the 4 of the 8 killing spinors, what you find is that the mass of the black hole equals the charge. Okay, which of course is as it should be based on the supersymmetry algebra. I'm saying this is a different type of analysis of this type. There's some differential equation you write down, you have to solve that, and that also gives you the same limit. Okay, these kind of black holes are called extremal black holes. Okay, so maybe I want to discuss that a bit to give you a sense of what black hole solutions we are talking about. Okay, any other questions so far? So I want to discuss extremal black holes a little bit.
Sorry, maybe one.
Please.
So extremal black holes are some subset of BPS black holes, or
Okay. All right. So very good. It's the other way around. So these words. So BPS. So there are 3 words which we are using: BPS, supersymmetric, and extremal. And oftentimes these are used interchangeably, but they're not. So I'll just try to tell you what is what. Supersymmetric states or black holes comes from the algebra. Okay, it just means that the supercharge should annihilate the state, or in this case, the solution should preserve some number of killing spinors. Okay, that's what supersymmetric means. The phrase BPS, that's an acronym. These are the 3 names: Bogomolny, Prasad, and Sommerfeld. That a priori doesn't have to do with supersymmetry. Okay, so what those people were studying was, in fact, not just in black hole, even in gauge theory. They're studying configurations of fields. Maybe I'll give you an example. Take gauge theory. Okay, F mu nu, F mu nu. Suppose you have an action of this sort. Okay, and then you write F plus minus mu nu is F mu nu plus epsilon mu nu rho sigma F rho sigma plus minus. Okay, these are the self-dual and anti-self-dual components of the gauge field. Okay, now Maxwell's equations. Maxwell's equations are second-order equations in A mu, right? But you can ask, are there solutions of this system where you have F plus equal to 0, say, or F minus equal to 0? Okay, these are some special type of solutions, and it turns out that firstly those are first-order equations because F is first order. Then it turns out that this you can essentially write. So now I'm being a little bit imprecise. Okay, something like this. If someone can help me with this, I'll be grateful, but it's roughly something like this, okay? It's not really equals. And maybe let me think about this for a second. I don't want to make a wrong statement. It turns out that, let's see, one write it. So F is F plus plus F minus, that you can check immediately. So you write this as F plus plus F minus square. Okay, F mu nu is F plus plus F minus square. What I want to say is that there is an inequality of the type m greater than or equal to q, which naturally arises from self-dual or anti-self-dual configurations. Okay, let me not waste time on this now. Maybe in the break I'll think about it and write it out properly. Okay, that's what BP and S were doing. Okay, they were just studying. Yeah.
It is like an instanton.
It's exactly like the instanton equation, if you know what the instanton. Exactly. All right. Good. Now, what did we get here? Yeah. So BPS, the origin is here. Okay, they were studying equations of bosonic theories which happen to be first order, okay, which gave you some inequality, and when you saturated, those were nice. They had some symmetry properties. Okay, so that's BPS. And the third thing was extremal. Extremal comes from the study of black holes only. And what that means, so that's what I'm going to discuss now. Okay, what that means really is zero temperature. Okay, I'll discuss that in a second. Okay. And now what's the relation between these three? So both BPS and extremal in the respective regimes are more general. They don't have to do with supersymmetry. But if a theory is supersymmetric, it turns out that supersymmetric solutions which have regularity properties, good analyticity properties, are extremal or are BPS. Okay, that's why people use them interchangeably. So if you just study this equation, you find that the only good black hole solutions that you find are the extremal black holes. All right. So all right. So the simplest situation, simplest context is take Einstein-Maxwell gravity. Okay, just bosonic Einstein-Maxwell gravity. Okay, so there's a square root gr plus square root g f mu nu f mu nu. This we already discussed a bit in lecture 1. And look at the Reissner-Nordstrom black hole. Okay, let's say with electric charge. So you have d square is minus f of r dt square plus dr square over f of r plus r square times that, where f of r was 1 minus r plus over r times 1 minus r minus over r. Okay, and remember that r plus minus was m plus or minus square root of m square minus q square. Okay, let's say this is only electric charge. And this shows, so this is completely bosonic, it's just Einstein Maxwell. And here you see that the regularity shows that m greater than equal to q. And when m equals q, there's something special. This we saw in lecture 1. There's something special, which is that r plus equal to r minus, and that the temperature was 0. Okay, so m equal to 0. So extremal m equals q, r plus equals r minus. And this is temperature equal to 0. This we saw in the first lecture. And the entropy turns out to be, remember the entropy is the area of the horizon. The area of the horizon, it's something like r squared dimensionally. So it should be a quadratic function in m and q. But now m is determined in terms of q. And turns out it's just very simple, just pi q square. Okay, all of this we did in the first lecture. I'm just reminding you. Okay, this is extremal. Now it turns out that if you study pure, if you study the simplest supersymmetric theory of gravity, so pure n equal to 2 supergravity, what that means is that there's g mu nu, a mu, and some fermions. Okay, there's one gauge field, metric, and some fermions. Okay, turns out there's a supersymmetric theory of gravity you can write, whose Lagrangian is precisely the bosonic Lagrangian is precisely Einstein-Maxwell. Okay, so this is the bosonic Lagrangian. Okay, Einstein-Maxwell just means square root g plus f mu square. It's the simplest sort of minimal thing you can write. So the way this is said is that this Einstein-Maxwell system can be embedded in a supersymmetric theory of gravity. And now you have these solutions, you have these black hole solutions. You can ask, do these solutions preserve any killing spinors? Now there are spinors, and therefore there's a killing spinor equation. And it turns out that the supersymmetric, so supersymmetric black hole solution, okay, which means that preserve killing spinor, is only possible at the extremal point. Okay, so you ask, if you write down this metric and demand to solve that killing spinor equation, you find it's not possible unless r plus equal to r minus, and then it's possible, and that preserves 4 of the 8 supercharges. N equal to 2 means there's 8 supercharges. Okay, so that's just to give you a sense of what these black holes look like. Now it turns out that in string theory, so now you can ask, can I embed this in string theory? That's what I want to do, because I want to match with this kind of that's where I'm going. I want to match with this microscopic description. By the way, this reference I should have said here. So this is Friedman, Van Pruyen. The section number is, well, it's 22. You can read chapter 22 for all of these things. And especially 22.4 and 22.5. Okay. So now you ask, how is this realized in string theory? All right. So you want a 4-dimensional n is at least 2 supergravity. Okay. Now you can ask, well, take those compactifications that we listed there, either a torus or K3 times T2 or a Calabi-Yau. You ask, what's the low energy effective action? And turns out the low energy effective action is something like this. It's like an Einstein-Maxwell theory. Except that fermions. Okay, except that it's very hard to realize theories with only one gauge field. Typically in string theory, when you do the compactification, you have lots of gauge fields and you have scalar fields. It's almost inevitable that you get that. And the Lagrangian changes a little bit. You don't have to, so Einstein Maxwell would have been just R minus F mu nu with just one gauge field and nothing plus fermions. Okay. Here what happens is that there are also scalars and there are many gauge fields. So I runs from 1 to something and A also runs from 1 to something. And the crucial point is that there is this kinetic mixing. The kinetic term of the gauge fields itself depends on the scalar fields. Okay. That's what string theory, when you study string theory, that's what happens. Okay. And therefore, now when you write the black hole solutions, so now you can write black hole solutions, the same type of story, that there are some solutions which are preserved supersymmetry, these are extremal. But now the entropy formula, which was just pi q square, so now you study supersymmetric, which means extremal black hole solutions, the entropy formula turns out to be something like this. There's a function called z, but this is a different z, some z of gravity, which depends on the electric and magnetic charges and on the scalars, and you have something like this. Okay, so let me give a sense of why this happens. When you had pure Einstein-Maxwell gravity, this was 1, and there was only one gauge field. Okay, then you get S equal to pi times q square, where q was the charge of that gauge field. Okay. Now, because the kinetic term itself is not canonical, you have to diagonalize this. Okay, you have to ask, what is the correct charge if I want to think of the charge of one gauge field? So you have to diagonalize this whole kinetic term, which depends on the scalar. And that's why the effective charge that appears here is a function of the charges and of the scalar fields. Okay, so roughly there's a diagonalization problem. This is not very difficult at all to, when you actually, it's just that it takes a bit of time to write down this Lagrangian and do this diagonalization. That's given in this book in a lot of detail. Okay, yeah.
Is not this g of pi is constant for n equal to?
No, it's some function for n equal to 2. So sorry, the keyword here is pure. Okay, so sorry, maybe I say that. In fact, I wanted to say that. So supergravity necessarily coupled to matter. Okay, that's the point. That there are always gauge fields and scalar fields which appear. Okay. Yeah, is that clear?
Sorry, so the scalar field here is the constant, right? In the entropy of the black hole. The phi in, yeah.
No, the scalar, so the area, I was going to say one more thing. I think you're anticipating something in a second, which I'm going to say in a second. Okay, so there's some function called, so let me say it this way. So before writing the entropy formula, let's say Q, the effective Q equals this. Okay, let me make that statement. Okay, that comes from diagonalizing this term. Okay, if you take the black one, measure the charge at some radius r, you get a function of the actual charge of the black, all the charges, this will be some qi, pi, and the scalar fields. Okay, that shouldn't be hard to imagine because of this mixing. Okay, now what happens is that when you go close to the horizon and you ask, what's the actual area? It turns out that this. So this is something very beautiful, and I would have liked to spend another lecture on this, but meaning it's accessible and it's a nice thing. But I don't want to do that. So this is you can read this section in the book, okay, in the supergravity book. What happens is that the scalar fields at the horizon, all the scalar fields are completely functions, are also determined completely by the charges. So what that boils down to is that Z black hole can be written like this. It's pi of Z horizon of Q and P. square. So there's a certain function that the theory gives you, which, as I said, it's not magical at all. You can just literally diagonalize this and ask what's that function at the horizon, and you find that the entropy looks like this. Okay, so I'm not giving you just for lack of time, but that's something you can study in this book. Okay. Now, what I do want to say is, what does that function look like? That function z, the central charge function, so z grav at the horizon. Okay. Depends on the theory that you're studying. Clearly, it depends on this function g and so on. It turns out that, as I said, there's a very beautiful story. There's one function called the prepotential function which determines all this and so on. I urge you to study it. So for the moment, I'm sort of just giving you some bits and pieces. But let me say the following. For n equal to 8 string theory, that function is completely determined by the supersymmetries. Okay? So this, for n equal to 2 theories, this function depends on which Calabi-Yau you compactify on. For n equal to 8 theories, there's only one theory. There's only T6. So that is just some given function. Okay, so if you ever see n equal to 8 supergravity, you should think of a Lagrangian like that with some fixed function g. Okay, with some specific function g. And that translates to some specific central charge function such that S black hole is pi times square root of, so let's take a black hole which preserves 1/8 supersymmetric, 4 supersymmetry, so 1/8 BPS black hole, and let's say it has charges Qi and Pi. Turns out that there is a certain inner product so there's a certain inner product on the charge lattice. Okay, I'm not, as I said, there's a lot of details which I'm not giving, but all of this is determined by the Lagrangian. That's what I want to say. If you just study it at home for 2 hours, you can come back and ask me, and you'll see what this is. Question.
You said that supergravity might be coupled to matter. Do you mean also supersymmetric matter?
Yes, it's all supersymmetric. So let's take the example we're studying. So it's n equal to 8 supersymmetry. That means that it cannot have any matter, right? That everything is in the gravitational multiplier. Yeah. So the whole. So let me tell you what so the field content written like that would be g mu nu. There'll be some I equals 1 to 28, and then be lots of scalar fields. I forget how many, and lots of fermions. Okay, and as you correctly say, for n equal to 8 theory, it's very simple because the whole thing is just determined by supersymmetry. There's no choice. Once you know that you have a metric and n equal to 8 supersymmetry, it just gives you this representation. And the same fact also gives you the Lagrangian. It just fixes the Lagrangian.
But when you say matter, do you mean everything beyond g mu nu, or do you mean more multipliers for n equals 2 or n equals 4?
So that depends on the theory. So maybe it's not clear what I said. So n equal to 2, let's do n equal to 2. N equal to 2 means that the gravity multiplet looks like that. Okay. Then you can have matter multiplets. Okay, like a mu, complex phi, and fermions, and then you can have some hypermultiplets and so on. And then you have a choice, and that choice is given to you by the Calabi-Yau compactification.
You necessarily have those.
Yeah, let me just finish. So in n equal to 2, you have a choice. You can say you can have a theory of pure supergravity or supergravity plus matter. Okay, or let's look at the bosonic Lagrangian. You have gravity plus one gauge field plus other matter multiplet. For n equal to 4, it turns out that this is the multiplet. I mean, you probably know all this. This is in the gravitational multiplet, and then there can be more n equal to 4 matter multiplets or not. Okay? But if you look at it from the point of view of the bosonic Lagrangian, there is this minimal n equal to 2 multiplet plus necessarily one gauge field and one complex scalar field. Okay? It all appears in the multiplet. Same thing for n equal to 8, you have this whole thing. So from the point of view of the bosonic Lagrangian, there's square root GR plus necessarily lots of Maxwell fields plus necessarily lots of scalar fields. That's all I meant.
So I still didn't understand. If you mean by matter, you mean what's constrained by the gravitational multiplet or not? You say you have the choice, but then on the other hand, you say necessarily has matter.
Yeah, so what I mean is that if you write n equal to 8 supergravity, yes, the Lagrangian is of this form, and I say necessarily means that I runs from 1 to some number nv, which is greater than 1. That's all I mean by necessarily. That necessarily goes beyond the pure supergravity, n equal to 2 supergravity. That you have that, and a runs from 1 to some other number.
Okay, so it's with respect to the n equals 2.
Mm-hmm. Yeah, that's what I said. Okay, good. Other questions? All right. Okay. The point I wanted to make is that the only point I wanted to make is that in Einstein-Maxwell theory, there's a very simple notion of extremal, which just has m equals q, whereas in more complicated theories, there's this kinetic mixing. But nevertheless, the notion of extremal has a very similar algebraic flavor, that there's a charge, effective charge, which is this absolute value of one function, but it depends now on all the charges and all the fields. But at the horizon, the field dependence goes away, but you still have a dependence on all the charges. Okay? Now in n equal to 8 theories, the way, if you translate all of this, you get an entropy like this, okay? Which is again effectively some pi times some quadratic function of the charges, but this quadratic function now depends on this whole vector of charges that you have. Okay? Where this vector is 28 dimensional. Okay, so I 1 to 28. Okay? And the way this inner product works, the way this Z works in n equal to 8, is that in order for this to be non-zero, implies that you must have at least, so q square, just to give you a sense, q square is something like q, the metric that I'm talking about, let's say there's only two, how should I say it? The metric is kind of off diagonal. Okay, so what that means is that you need at least 4 charges for this to be non-zero. Okay, so you need at least 2 magnetic and 2 electric charges in order for the entropy to be non-zero. Okay, so this whole discussion of the last 10 minutes was to make this statement, that the entropy again has a quadratic function, is a quadratic function of the charge. But in string theory, you need at least 4 charges in 4 dimensions for the entropy to be non-zero. So if you write down a solution of the theory with some arbitrary number of charges, and you want a black hole with some non-zero horizon area, then this must be non-zero. Okay, and the way it works is that you need at least 4 of them. Okay. Yeah, so it's like, so in the n equal to 2 supergravities, it's actually symplectic, right? So you'll see why it's off diagonal. For n equal to 4 or n equal to 8, the corresponding duality group is larger. For n equal to 8, it's some E77 of Z or something like this. And that group invariant turns out in the n equal to 2 notation to be symplectic, which means that,
Can I ask?
Yeah, which means that, just one second, which means that these, sorry, there's no dot here, q square times p square. So q square must be has the form q1, q2 plus q3, q4, etc. And similarly with p square. Somebody asked the question?
Yeah.
Yeah.
Sorry. I think I'm missing something.
Yeah.
So, field vector squared is also a vector.
Yeah, so, no, it's not a vector, it's a, so let me see. So, what I'm saying is, there's a certain inner product, so there is Q square is something like this, Q1, Q2 plus Q3, Q4, okay? Something like this. So if you have a vector of charge, some metric which gives a form like this, similarly P square and Q dot P. And if you take, for simplicity, you take a black hole where Q dot P is 0, and what you're left with is Q square times P square. They're both scalars. Yeah? Okay.
So in that formula, yeah, you arrange the inner product.
Yeah. There's no dot there, yeah, so that was a mistake. Good. And the microscopic, what time is it, by the way? Electric and magnetic charges, 28 of them. And there's a certain inner product which defines Q square and P square and Q dot P. And you can choose charges such that Q dot P is 0. So you have the entropy is pi square root of Q square P square. Okay? And the inner product is such that the Q square means that it's really Q1 times Q2. Okay? And P square is P1 times P2. Okay? So you need at least 4 charges to make a black hole in 4 dimensions in string theory. It's a technical point, but this was somehow in the beginning, and even now this was what took a while to understand in the history. Like why can't you just study black hole, your favorite black hole solution, and find its microstates? The reason is that it's difficult to do that in string theory. So for instance, the Schwarzschild black hole, string theory admits Schwarzschild solutions, but you don't know what the microscopic description is, right? Because it's not supersymmetric. So even if you know what the mass is, then you have the same problem as for the fundamental string. The formulas don't agree, but they're not meant to agree because they're written in different regimes. Then you look at supersymmetric black holes, say, well, why not the simplest supersymmetric black hole with 1 charge? Okay. Then you just study S equals pi Q square, study states with 1 Q. It sounds like a much simpler problem. The issue is that those solutions are not known in string theory. It's very difficult to construct. So the game, so what Sen and Strominger realized is that you can instead just study string theory, ask what it gives you, and see if there is a microscopic description, and try to find the smallest, sort of simplest description on both sides. Okay, so that's roughly the game, and this turns out to be the simplest thing. It's four charges in 4 dimensions. Okay, Strominger actually were looking at 5-dimensional black holes, which is closely related to this. Sorry, should I start? Yeah. Okay, so the microscopic description in string theory is like this. It's there's R13 times S1 tilde, T4. Okay. So I'm writing T6. I'm singling out 2 circles. Okay. And the microscopic description of these 4 charges, these 4 minimal charges, is like this. There's a D1 brane. So in R3 they're all point-like. In D1 brane it wraps the S1. And you can have Q1 of them. Then there are D5 branes, which are again point-like in R4. It wraps S1 and T4, and you can have Q5 of them. Then you can have some momentum excitation on the S1. Okay, there's a string, some D1 string, and you can excite some momentum, and that has quantum number n. That was the black hole that, so in 5 dimensions, in fact, if you sort of study the same story, it turns out that that's enough to make a black hole with big horizon. But in 4 dimensions, you also need one more charge, which you can choose to be a Kaluza-Klein monopole wrap on S1 tilde. Okay. Now, I don't know if you know what a Kaluza-Klein monopole is, and again, it will take me some time. So the fact is that that's not going to be very important for us in this story. And again, you can ask me during pizza what that is. It's a certain type of charge in string theory. It's essentially a magnetic duo to momentum, if that helps. Okay, and we'll just take it to be 1, and in fact, it's not going to affect any of the discussion that we're going to have. Okay, so effectively what you have is it's called the D1 D5 string, which wraps S1. Okay, so think of the T4 as some small thing. So the D5 branes wrap T4, so they become point-like. So D5 means there are 5 plus 1 dimensions, so the plus 1 is time. So it wraps 4 here, there's 1 left, and there's 1 of this, and both of them wrap the S1. Okay, so there's some kind of stringy object in string theory which is wrapping this S1. Okay, and on that there are n units of momentum. Okay. All right. Then, as I said, this Kaluza-Klein monopole should also be taken into account, but that's not going to be important for us. The KK monopole not important today. Okay, it's because it's not that it's not really important. What you have to do is to now study BPS excitations of all these charges. But this I can explain later. Okay. Maybe I should give references. That you should look at Gayotto, Strominger, and Yin 0503217, I think, and David and Sen 0605210. Okay. All right. Please.
First of all, what do the crosses and what dots mean?
So dots means that in R13 they're all point-like, right? We want them to be point-like. So there's some point-like thing in 4 dimensions, and when you crank up the coupling, they'll become a black hole, right? The black hole, after all, the charges are like that of a point-like object. It's not extended in 4 dimensions. This means that, so D1, what is a D1 brane? A D1 brane is an extended object in string theory, and it's extended in 1 dimension plus 1 time. The 1 space dimension, you wrap it around S1. That's what this means. D5 brane has 5 extended directions. You wrap it on S1 and on T4. Momentum is not an extended object. You have to ask in which direction is the momentum given, and that's also in S1. Okay, and then KK monopole, I said I don't want to discuss. Yeah?
Yeah, and the last column?
Last column is the last row, you mean this. The last column is the number of branes. So this is, so you can have a brane which wraps S1, and again and again and again, it can wrap it Q1 times. Or you can have Q1 branes. These are more or less the same thing. Okay, it's the wrapping number of the brane. Q5 is the wrapping number of the D5 brane, and P is the number of units of momentum around the circle. Okay, so the physical P will be some integer, and all of these are integers, will be the integer n divided by the radius of the circle. All right, other questions? Okay, now okay, I want to get to the counting. All right, maybe I can go through this. It's useful because we spent a lot of time on supersymmetry. So if you look at supersymmetry, look at n equal to h supersymmetry. So these are preserved supersymmetries and broken. Okay. This 32 supercharges, if you put a D1 brane, that preserves 16 of the 32 supercharges, as I hope all of you have studied, and it breaks 16. Then if I put a D5 brane on top of that, let's do D5 first. And then if I put a D1 on top of that, that breaks this down further to 8. Remember, D1 and D5s are both half BPS objects in string theory, but if you put both of them, they preserve different, they don't preserve the same half. Together they preserve 8, and this will also be 8. And then I can study momentum excitations on this effective string, effective D1, D5 string, that preserves 4. But I want to say that a little better, that before putting momentum excitation, and then there is KK. Okay, so there's KK which doesn't change the supersymmetry. You can also, yeah, leave it like that, D1, D5. Okay, so KK, I'm not being very precise, but it's somehow it works out. Is the statement. Now, this much, if you just look at this D1, D5 system, so the goal is to somehow count the number of supersymmetric excitations of the system. Now you really want to count. Okay, that's where we're heading. This is the last chapter of this whole story. The description of the effective D1, D5 string is given by a two-dimensional, so it's a string, okay, it's a string which means it's 1 plus 1 dimensional, so it's a two-dimensional 4,4 superconformal field theory at low energies. Okay, so that's again a whole, this line contains a lot of physics. It says that if you take this string theory and put D5 branes and D1 branes and then study their BPS excitations, or actually any low energy excitations, those turn out to be captured by a certain superconformal field theory with central charge. Let's actually say what that theory is. It's known what that theory is. That theory is the symmetric product of Q1, Q5 of T4. Okay. This statement is in the original Strominger-Waffer paper, and then another one, so that's 96, and one soon after by Maldacena, Strominger, Maldacena, Moore, and Strominger. Okay, in 98, I think, 99. Okay. Right, what does that mean? Symmetric X just means, this is a mathematical notation, symmetric N of X. If you have any object X, it could be a manifold or anything else, this means you take N copies of that and then you quotient it by the symmetric group on N letters. So the discrete symmetric group on N letters. Sn is the discrete group, which if you have N points, you look at all possible exchanges. That's the symmetric group, and that's the quotient. Okay. Again, the details are not super important. What is important is that the number of degrees of freedom is so many. It's Q1, Q5 copies of T4. Then there's some quotient. Okay, but that quotient doesn't change the number of local degrees of freedom. Okay. So this T4 has 4 bosons. So this has 4 bosons. T4 has 4 bosons and 4 fermions. Right? And Q1, Q5 copies of that will have, sorry, I want it to be small, Q1, Q5. Q1, Q5 copies of that will have 4 Q1, Q5 bosons and 4 Q1, Q5 fermions, these copies. And so C will be 4 Q1, Q5 from here, plus 4 Q1, Q5 by 2, because each fermion has central charge 2. So the central charge will be 6 Q1, Q5. Okay. So that's the description of the theory. So that's the idea, right? You make some configuration in string theory which has the same charges of the black hole. And you ask, how do I describe this theory, and how do I then enumerate the microscopic states? Okay, so this is the theory. And now if you look at the supersymmetries, indeed this has 8. The theory so far has 8 it preserves 8 supersymmetry. That's what it means. 4,4 means that if you have a string, there are left movers and right movers, exactly like in elementary, like in fundamental string theory. And 4,4 means that there are 4 supersymmetries on the left and 4 supersymmetries on the right. Okay. So if all of you studied fundamental string theory, the analogous statement there is that the fundamental string has 10 bosons and 10 fermions on its worldsheet, and it has 16 supercharges on the left and 16 on the right. Okay. There is some effective string theory with so many bosons, 4 Q1, Q5 bosons and 4 Q1, Q5 fermions, and with 4 supercharges on the left and right. Okay. And this momentum, finally, you make it purely left moving. Okay. Which means that the 4 supercharges on the right are always preserved. So 4 right moving supercharges preserved, and what that means is that the 1/8 BPS states are left moving states of this theory of this symmetric product with left moving Hamiltonian equals n. Okay, so when you identify the charges, it turns out that this momentum charge becomes the left moving Hamiltonian. So I'll just repeat that. So we started from some kind of a space-time description of these branes, and then we want to zoom in and ask, what is the theory in which we are going to count? That theory is some theory of that effective string. Okay? And that theory has so many bosons and fermions. These are two-dimensional bosons and fermions. And because it's an effectively free string theory, there are left movers and right movers. So there's a left moving Hamiltonian and a right moving Hamiltonian. So HR is 0. Okay. And there's a left moving supersymmetry and 4 supercharges and right moving supercharges. And all the left moving supercharges are broken. That brings 8 to 4. And what you're left with is some right moving supersymmetric ground states and left moving excitations, and then there's a final part which you have to also see. So the left moving Hamiltonian is equal to this momentum. Okay. So all of these statements are sort of, it has to be studied, but that's essentially what these people did. Okay, so until now I was trying to sort of make statements without fully explaining it, but trying to give you some sense of where that is coming from. And after this, I want to do one last thing in these lectures, which is completely self-contained. Okay, because I think it's easy and you should all see it. Okay, but any questions about this? Yeah.
What kind of fields are those target fields into the target space?
Yeah, so it has some target space, which is this symmetric product Q1, Q5 of T4. Right? That's the description.
Oh, it's the, okay, this is the target. So that thing about I think about Minkowski space anymore?
Say again?
Minkowski space, it doesn't have Minkowski space, it's the target space.
No, the target space is not Minkowski space. It's this target space.
It's the internal space with respect to Minkowski.
It's not a fundamental string. So there's some effective D1, D5 string, and you have to study its oscillations and ask, what do those oscillations describe? That's what Strominger and Waffa did. Actually, Waffa had done this before, a couple of years before this. It's described by some gas of instantons inside this D1, D5 string, whose effective target space is this symmetric product of T4. Okay? Okay, but today, now the rest of the, how much time do I have? What time is it?
15 minutes
To
to 12.
12, okay, so I'll finish by 12:10 or so, max. Okay, so even if all of this you did not understand, try to switch on again. And now we're going to study this problem. There's an effective string, okay, a free string, and the first thing, a free string means that there's a decoupling of left and right movers. Okay, that all of you must have seen. And in that string theory, we know that there are so many bosons and fermions. We want to ask how many states are there which carry some left moving energy n and right moving energy 0. Okay, so it's a simple problem. Maybe many of you have seen this, but I want to do it again and derive what's the density of states. Okay, that's very useful, and you'll see, you'll probably see this if you do any such problem. You'll see this kind of a manipulation. Okay, so how to calculate the degeneracy of such states? Any other questions so far? Before I tell you because I'm switching style a little bit, so any questions about the statement? So far we have that this some 1/8 BPS theory, this is black holes. So oftentimes in seminars I begin with this statement, but I was trying to give you a little bit of details that in string theory you have two pictures of black holes. One is a black hole as a solution, the other one is some ensemble of microstates. And the best understood example is this one, that there's a solution of 1/8 BPS black hole theory. I should have said something. That 1/8 BPS black hole has 4 charges, Q1, Q5, and Q square is 2Q1, Q5, and P square is 2 times n times 1. And therefore the entropy of the black hole is, remember, it was pi times square root Q square P square, so it's 2 pi times Q1, Q5n. Okay, so that's the black hole solution. Okay. And then there is a microscopic configuration with the same charges, Q1, Q5, and n. Okay. Which is that, and you know what theory describes the microscopic excitations. Now we want to count the number of states as a function of Q1, Q5, and n. Okay, that's the story. All right. Okay. Huh? 2n times 1. So remember, this was some number of kk monopoles, which were taken to be 1. So remember, I just said that because it's quadratic, so there must be at least 2 charges. We took that to be equal to 1. Okay. All right. Now, please sort of try to make this change in your head. So we're going to do this example of how to calculate. So let's do a toy example. So let's say you have only one boson. Okay, let's call that boson X. Okay, so this is a function of sigma and tau. These are the string coordinates, sigma and tau. Okay, and it's a free string. So free string means that you have minus d tau square plus d sigma square of x equals 0. Okay, that's a free Laplacian. That means that x can be written as x0 plus x left, which is a function of only x minus, and x right, which is a function only of x plus, where small x plus minus is t plus minus sigma. Okay, so those are the left movers, those are the right movers, and that's the 0 modes. Okay, this I want to go slow because here I want all of you to be really, like, if you don't understand even a single thing, stop and complain. Okay, so just the Laplacian equation dt, so you can factorize this into dt. This is the same as dx plus dx minus. So firstly there can be linear modes, which are the 0 modes. X naught plus sigma p sigma w plus tau times some tilde. Okay, and here you can have oscillator modes of x minus and x plus. All right. So x left as a function of x minus is sum r equal to 1 to infinity 1 over square root 2r times ar e to the minus I r x minus plus ar dagger e to the plus I r x minus. Okay, these are the creation and annihilation modes associated with each oscillator. Where?
What is the letter that you're summing?
R. This?
Or rho?
R.
It's an R.
R. Okay. Similarly, there's an x right. I won't write x right because we want to study left moving excitations. Okay. So now we want to quantize it. So quantize that. Okay. So you get h left. So these are all free. So these are harmonic oscillators of frequency r. Right? So h left is sum r equal to 1 times r dagger ar plus half. Okay. So far so good. Now, so for each r, Z plus, this is a harmonic oscillator of frequency omega r equals r. Okay, good. So now you calculate the thermal trace. Okay, what we want to do is to calculate how many states are there with some given energy n, and in order to do that you look at the canonical ensemble, you calculate the thermal state and then you do a Laplace transform. Okay, this is the usual way to do it. So you do a trace. So you want to study Z as a function of beta, which is trace over the full Hilbert space times Q to the HL, where Q is e to the minus beta. Okay. So if I can calculate this trace, I know that this will be equal to sum dn Q to the n, and if I know this function, then at energy n, I can invert this equation to calculate what is dn. Okay, so it's often easier to calculate the canonical ensemble. So once I know this trace, I just read off the nth coefficient in Q, and that gives me the answer that I'm looking for. Okay, any questions so far? Good. So how do I do it? If I have a harmonic oscillator of frequency W omega, then the thermal trace of that is Q to the, so there's a zero energy state, okay, then there is energy 1 to, occupation number 1, 2, 3, etc. Okay, so these are the states of the harmonic oscillator, okay, plus the 0 point energy. So that gives Q to the W over 1 minus Q to the W. Okay, and therefore the full, let me call this ZX. Okay, ZX, you put together all of the, so these are all decoupled. So in the canonical ensemble, you just multiply the partition functions. So that's just product of R greater than equal to 1, Q to the R by 2 over 1 minus Q to the R. Okay. Now, this needs to be well defined because this gives, the numerator gives q to the sum r equal to 1 to infinity of r. Okay. The denominator is fine, it's product of 1 minus q to the r. Numerator is that, and that sum is usually done by some zeta function regularization method. You can regulate it in many ways. If you look at the physics, it's clear that this has to be a finite object, and zeta function gives you, so I should remind you, zeta, remember zeta of s is sum of 1 over n to the s, n equal to 1, and so if I want sum over n, I want zeta of minus 1. So sum over n equals, doesn't mean equals, it means that you should instead take it to be zeta of minus 1. So there's a half here, of course. Okay, so it's half times zeta of minus 1, which is minus 1/12, so you get q to the minus 1 over 24. Okay, so this whole thing, so let's bracket, so this is equal to product, so it's equal to 1 over q to the 1/24th times product r greater than or equal to 1 minus q to the r. Okay, and that's precisely the Dedekind eta function of I beta over 2 pi. Okay, that's the Dedekind eta function. Okay, any questions so far? All right?
Eta is?
Eta is the Dedekind eta function. Okay, that's defined by these formulas. Product, q to the 1/24th, product over all integers, positive integers, 1 minus q to the integer. Okay. All right. Now we want.
So what's the argument of the eta function?
I beta over 2 pi. Let me write it again. So we have trace zx of beta is sum d of n q to the n equals 1 over eta of I beta over 2 pi. Remember, eta is defined like this. Eta is a function of so-called q equals e to the 2 pi I tau, and eta of tau is product is q to the 1/24th times product r greater than or equal to 1 minus q to the r. Okay, that's the canonical definition that I'm using. Okay, so tau, so because I want q equals e to the minus beta, the argument is I beta over 2 pi. Okay, good. Let me even write it like this, e to the minus beta n. So d of n is therefore given by the Laplace transform d beta e to the beta n z of beta. Okay, this contour is chosen as the inverse Laplace transforms. Okay, this contour is chosen to make the as in the inverse Laplace transform. All right, but please stop me if any of these terms are not familiar. As I said, this part should be completely clear. All right, there are many ways to write this. You can also write this in terms of q as a complex variable and write this as a contour integral. That's another way to write it. Or you can write it in the tau variable. Okay, they're all completely equivalent. This is the easiest because there's just one real parameter. Okay, good. Now let's work this out. Maybe I've already done it here. So the main point now is as n goes to infinity, as n goes to infinity, how should I do it? As n goes to infinity, you want to try to estimate this. Okay? And whenever you have such integrals where you have e to the some beta n times some function of beta, the way to estimate it is, the best way to estimate it is use the saddle point approximation. Okay? So as n goes to infinity, beta should go to 0. Okay, because that's what the saddle point gives. I mean, maybe I should say it maybe here. That sometimes it's easier to think about this also in the tau variable. You might be more comfortable with this, e to the minus 2 pi n tau times some function of tau. Okay, or you can think of this as a contour integral, dq over q to the minus n, some fgh. Okay, they're all completely equivalent. So by saddle point, of course, what I mean is I think of this as a complex variable. That's what I'm doing in the Laplace transform. And I want to look at the saddle point or stationary phase, depending on which formula you use, you have to. But essentially, it's always the same thing. What you have to do is to ask, where is the saddle point of this whole thing? Okay. So as n goes to infinity, use saddle point. Okay. Or stationary phase or Laplace or whatever you call it, and therefore you want to know. So already you have an estimate that as n goes to infinity, beta should go to 0. So you want to know the behavior of this function as beta goes to 0. Okay, that's your main thing. If you know how this function behaves as beta goes to 0, then you can easily do the saddle point estimate. Okay, now. So z was 1 over eta, okay, of e to the minus beta. So as beta goes to 0, q goes to 1, because q is e to the minus beta. Okay. So if I just put z of beta, if I just stick in beta equal to 0, okay, then I get a divergence. I get 1 over 1 minus 1. Okay, so there's divergence. Okay, so it diverges. I mean, lots of divergence. Okay, so the question is, in what way is it diverging? So we know that it must diverge. So the question is, that means that you shouldn't stick in beta equal to 0. That product formula is, this is for q less than 1. Okay, so when beta equal to 0, you're going to the edge of the unit disk. So it means that there's some divergence close to this point, q equal to 1. And the question is, how does the function diverge? You can put it on a computer and check this. Okay. Now the nice thing is that this function is very well studied. It's what is called a modular form, which means that there's a relation between eta of minus 1 over tau and eta of tau, up to some little complex number. So eta of minus 1 over tau is some root of unity times tau to the half times eta of tau. Okay. And that's an amazing equation, because if tau goes to, so let's do it in the beta variables. It means that, let's do it here. If tau goes to 0, that means q goes to 1. That's when we don't know how this behaves, right? Because this product formula diverges. But this side of the equation, if tau goes to 0, the argument goes to I infinity, and therefore q goes to 0. And q goes to 0 is trivial what the expansion of this equation is. It's just the first term, and all of these become 1. Okay, so I'll say that again. So eta, I'll write this out now. So eta of I beta over 2 pi, which we want, equals eta of tau with that map, which is equal to tau to the minus half times eta of minus 1 over tau, okay, by this modular equation, times some root of unity. I'm not writing that here. And that's equal to, I put back beta there. So I'll stop writing constants as, so up to a constant times, tau was roughly beta, so it's beta to the minus half times eta of I 2 pi over beta. I'll continue here. Equals q tilde to the 1 over 24th times 1 minus q tilde, 1 minus q tilde square, dot, 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 where q tilde is e to the minus of that. So it's e to the 2 pi I times I 2 pi over beta. So this is e to the minus 4 pi square over beta. Okay, and this goes to 0 as beta goes to 0, and it goes to 0 exponentially fast. Okay, so that's the main trick, that you have this modular behavior. So this is the main equation, that the tau goes to 0 limit, that the tau goes to 0 behavior of this function is the same as the tau goes to I infinity behavior of this function, where it's very easy to calculate, and therefore you get when you calculate it. Okay, so you get, as beta goes to 0, z of beta goes beta to the half divided by q tilde to the 1/24th times 1. I just call this 1 because everything else goes to plus O of e to the minus 1 of beta. Okay. So exponentially fast is equal to that. So up to exponential corrections, which you don't care about, you get a very good estimate. So let's do the estimate. So d of n, as n goes to infinity, is, so what is it? It's an integral of e to the beta n plus 4 pi square over 24. Q tilde was e to the minus 4 pi I square over beta. So this is just plus pi squared over 6 beta. Okay. So I've checked this at home, but just make sure that at home you do this yourself. It's a calculation. If you do these kind of things, you'll use again and again. All right. Okay. And now after that, you're very easily in business. So if you want to times beta to the half, in fact, you don't even care about that. Okay. So you can even remove this because it's the exponential behavior that's the most important thing. So saddle point. Where is the saddle point? So you minimize this, means n minus pi squared over 6 beta square equal to 0, which means that beta equals pi square root of n over 6. Okay, you plug that back, d of n. Okay, so you plug that back, and you'll get one term from here, and they're equal. That's what saddle point means. So you get e to the 2 times pi square root of n over 6 over n, I meant 1 over 6n. Beta goes there, 6 goes there. Okay, so pi square root of n over 6. Okay, that's the plus corrections. Okay, there are power law corrections from the integral and exponential corrections from the fact that we ignored those things. All right? Okay. Any questions so far? It's the last 5 minutes after this.
Can you read tilde?
Yeah. So you just want me to read it? It's
Yes.
2 pi I times I 2 pi over beta. And that's equal to e to the minus 4 pi square over beta. Okay. The reason that happens is because the way to remember it, the easy way to remember is always tau and minus 1 over tau. That's what modular transformation does. And tau, you have to first fix what is tau. We did that. It was equal to I beta over 2 pi. So that's minus 1 over tau. All right. Okay. Now, this was for one free boson. Okay, and I did this in great detail just to show you how it works. But in fact, the result is true much more generally. So more generally, you can say it both in mathematical terms as in and in physical terms. Let me state it in physical terms. If you have any conformal field theory with central charge C, okay, in this case C was 1, just one free boson, we have that D of n is, by a very similar set of arguments, is 2 pi square root of Cn over 6. Okay. So this is called the Cardi formula. Okay. You can imagine why that happens. It's just one boson grew like this. So if I have C bosons, I just get a C here. Okay, and then everything goes through. Okay, this part remains the same. Okay, and the physics of this Cardi formula is that so relates the high energy or high charge growth of states with the vacuum energy minus CO24. Okay, and the main equation in physics would be like this: Z of beta would be some beta to some power times Z of 1 over beta. Okay, it's like a high temperature, low temperature duality. And the way Cardi thought of it, which is related to this way of thinking about it, but slightly different. You should read Cardi's original papers. It's very beautiful. Is to think of a torus, and you have sigma and tau, and consider the two different. In the Euclidean theory, you can rotate sigma and tau into each other. Say what is space, what is time, and the two different notions give you these two different partition functions. Okay. Now, let's do it for our black hole, for our system that we wanted. So you see that so if you apply this now to this D1, D5 system, remember C was 6 Q1, Q5. Okay, so that means that D of n, as n goes to infinity, grows as exponential of 2 pi square root of Q1, Q5. Okay, and that's exactly what the black hole entropy was. Okay, so indeed, so you have log of D of n equal to S black hole of Q1, Q5 n okay. Of course there are corrections, but at least for large charges this is true. Okay, so this was sort of the goal of my lectures, that I wanted to tell you the ideas and calculations as much as possible for one example where you can see this, that the microscopic state counting reproduces the black hole entropy. All right. I'm essentially finished. I want to write down some future directions, but let me pause for questions, if there are any, or it can be over pizza.
So in this example, you didn't use any supersymmetry. It was just that there's on it.
Good. So that's not quite true. So I made it sound like that, but that's not quite right. So remember we said we were studying the supersymmetry. So there is this type 2 theory which has 32 superchargers, and then it gets broken to, by the D1, D5 system, it gets broken to 8, 16 and 8. And then this is kind of 4 and 4. And then you want to study momentum excitations which are left movers only, and the right movers are in the ground state. So there's some 4 superchargers. These states are annihilated by 4 superchargers. So they are supersymmetric states. But let me rephrase your question. That last time in the beginning of today's lecture, we said, well, we should study these indices, right? So, and I just did some counting formula, right? So how come there? So the answer is that, so I skipped some steps. When you study this CFT in the superconformal field theory, the thing we said last time we should study is what was it? B14, right? 28 zero modes. Okay. Remember, in type 2 theory, we're studying states with 4 superchargers. So it breaks 28 of the 32, so we have to study B14. Okay. So now you look at this string. So you have a D5 brane, which breaks 16 superchargers. That means that the 16 zero modes are localized outside the D5 brane. Then you put a D1 brane, same thing. Other 8 zero modes are localized there. So when you study the D1, D5 system, so there's 16 plus 8. So you have a D1, D5 string, and there are 24 of the fermion zero modes are localized outside the string. Okay, so you've absorbed 12 of the 14 of them, and you're left with 2 more fermion zero modes, which you have to absorb inside the conformal field theory. And that's exactly what you have to do, because now there's the right movers which still have 4 fermion zero modes. So there are 4 superchargers. So there are 2 complex fermion zero modes. So what you're really studying in this superconformal field theory is this. It's really the leftover part of B14. It's trace minus 1 to the F times 2, let's say F right square, or J right square, times Q to the N. Okay. So when you include this, then it turns out that indeed you're studying B14. So it's really the thing that you wanted to study. But the fact is that this is absorbed trivially, and this just is equal to the trace over the left moving Hilbert space of Q to the N, because on the right movers, all of this just becomes 1. And that's why we studied this type problem. Okay, well, it's a very good question. So it's really what we should be studying is what is being studied. Okay. In the old days when Strominger and Waffer were doing this, they didn't understand, I mean, implicitly they probably knew a lot of things, but it was not presented like this. And it was only after Ashok Sen's work that this part of the story was completely developed. Okay, so let me write, I mean, you should study the original work of Strominger and Waffer. It's absolutely beautiful, and it's one of the most creative things that I've seen in string theory, and one of the big successes of string theory. Right, I mean, the original problem of explaining the entropy of black holes was posed by relativists. I mean, it's a problem coming from GR. So this whole thing was a big success of string theory. Okay, so I'm just going to list some directions and topics. So for the first one is this entropy equal to index. It's so on one side is the kind of question Ali was asking, but on the other side is something that so here today we kind of saw why in the microscopic side there's a counting formula which is equal to an index. That index is preserved in gravity throughout the coupling constant space. It's an index in gravity, and then we argued last time why the fermion zero modes drop out. Turns out that there's a last argument which I didn't present. You have a trace of minus 1 to the F inside the black hole. And then there's some slightly more advanced arguments to show why that's also equal to the entropy of a black hole. I can explain over pizza. But you can study this paper I wrote with Sen and Davolkar and Gomsh, okay, which I presented. I gave the reference last time. Okay, so that's one set of things you need to fill. Then you can ask, that, well, we made lots of approximations, right? So we said in deriving this Cardi type formula, we said n has to be very large. What if n is not very large? Okay. Well, so you can study both sides of the equations when the charges are finite. Okay, this side is easy. You have a set of integers. I mean, you have this partition function. It's an explicit function, and you can just say what those integers are. But there's a nice analytic way to study that in the 1 over n expansion. So in the microscopic theory, so if you have these, so if the analytic number theory, so it's Hardy, Ramanujan, Rademacher expansion. If you Google this, you'll find a lot of literature. So there's a way to express the corrections on the left-hand side of that equation analytically in terms of the charges. Okay, it's a very beautiful piece of mathematics. This is almost 100 years old. This is from the 1960s. And it's actually a convergent formula. And on the macroscopic side, which means you can ask, well, okay, here there are corrections. What about this side? Okay. This side, I've measured the entropy, and it looks like that's all there is. Right? But it turns out that when the charges are not infinite, not very large, you're away from the thermodynamic limit. That means that the curvatures are not very small. That means quantum gravity effects start to kick in. So you have to study quantum corrections to the entropy formula. Okay, so quantum corrections to the Bekenstein and Hawking entropy. Okay, Bekenstein and Hawking worked in GR. Now you have to ask, what if there is a quantum theory of gravity? How do you start to solve this problem? Okay, again, in string theory, there's a lot of progress. Then, just to give you a sense, so there's one type of progress, like you study higher derivative corrections in string theory, coming from the string world sheet, and try to redo. Then there's questions of what is the correct formula for the entropy, because now you have to make sure that it obeys the laws of thermodynamics. I mean, each question sort of gives rise to more questions. Then there are questions of how do you do path integrals in gravity? Can you do it at all? Okay. So a lot of progress has been made. This review of sense that I pointed out last time is a good starting point. And then if you want more, you should ask me. Then I ignored this KK monopole. I said it's not very important for this, and it's not. And then there is, so that needs to be filled in. And then there's this issue of constancy of the index across moduli space. Sorry, before that I should say something here for the more advanced of you, that this side is some mathematical formalism, which is also very interesting to study. On this side, the progress is like this. So first, one kind of thing was initiated by Cardoso, DeWitt, Mohopt, and Capelli, where they were looking at higher derivative corrections of string theory and asking how that affects the black hole entropy. And the second type of corrections is like trying to really do loop effects in the background of a black hole. And both of these add up to eventually end up matching the corrections from this side. So there's alpha prime effects, loop effects. Okay, and then you can be brave. You can try to study this example, for instance, you can try to study with some kind of exact methods called localization. And that, if you're interested, that so you can look at my paper with Dabulkar and Gomes. This is 2010, 2011, and 2014. And more recently, this is Iliesu, myself, and Turiachi. Okay, so if you're interested in such kind of thing, I'll be very happy to discuss it. Okay, then constancy of index across moduli space. So we said that the index doesn't change. We had an argument, this is Witten's argument, why things don't change. But as Witten himself had understood, that argument breaks down, can break down if there are at special points in moduli space, so what he calls, there are states coming in from infinity. So the argument was that states always go in and out of the BPS spectrum in pairs. Okay. But that assumes some kind of normalizability conditions on all the wave functions. Sometimes that is broken, and that can happen at codimension 1 surfaces in moduli space. So there's this whole phenomenon called wall crossing. Okay. And that has to be studied, and for n equal to 4 string theory, already that happens, n equal to 4 string theory. Turns out that you have to be a little careful about that. That when you start counting, you expect to have some modular form of this sort, but you don't because of this wall crossing phenomenon. And quite miraculously, it's replaced by what are called mock modular forms. Okay, if you're interested in that kind of mathematics, again, there's a paper of Dabolkar, myself, and Zagier. You can look at that. And more, so then you should ask, what happens in for black holes in any, that was n equal to 8 theories, what happens in n equal to 4 theories, n equal to 2 theories. Okay, so there's one simple example of n equal to 4 has been studied. Murthy there has studied other examples. N equal to 2 is, people still understand very little because the black hole solutions are easy to write, but this counting problem is not so easy. You don't to control that. And then there's another possibility. You can also study black holes instead of flat space, you can study asymptotically ADS space. Okay, that's yet another direction. So I'm listing directions on which things have been done, and all of this relates to supersymmetric black holes only. Of course, there's a whole question of what happens when there's no supersymmetry. But even with supersymmetry, if the idea is to sort of have systems which you can control and study the details, there's a very rich story. I mean, multiple stories along these directions. Okay, but by and large, the lesson is that supersymmetric black holes allow us to control and study these problems, and it gives you an example where this Boltzmann equation for black holes can be studied and understood and verified in one theory. Okay, so I'll stop here. Thank you very much for staying through the 3 lectures, and you can always come and ask me questions, write emails, whatever. Thank you.